Nike says that 70% of runners feel their shoes improve performance. Starbucks promises the average wait time in their stores under 5 minutes. But are those claims really true or just marketing? That's where hypothesis testing comes in. We take a claim about a proportion or a mean, and then we use data to see if the evidence supports it. Sometimes we ask if it's higher, sometimes lower, or just different. That's the difference between one-sided and two-sided tests. In this chapter, we learn how to test claims for both means and proportions, and how to make decisions based on evidence, not just slogans.
Now we are going to look at the chapter in detail. So first we look at some terminologies. We have two terminologies here. One is hypothesis and another one is hypothesis testing. A hypothesis is a claim about property of a population. So we can make a claim about maybe the proportion, the mean, the variance, different quantity. And for this class, we just focus on proportion and the mean. So say we may claim that, say, the average screen time of people more than 1 hour a day, right? And maybe the proportion of people in favor of a new policy is more than 0.8, or maybe more than 80%, if we talk about percentage. And then in order to support the claim, we need an evidence base, right? The evidence base. So at that time, when you support your claim, and then you need to use some data, and you need to follow certain procedure. And here we say the statistical procedure to support the claim. Here at that time, we will perform in a hypothesis testing. So in example 911 here, we talk about Atlanta Water Quality Index, WQI in short. So here in this case, a researcher, he suspects that Atlanta water tap not drinkable. So say, he walk around the region and he tastes the water and he suspects that, right? So in order to prove that he correct, right, we need to translate it to the scientific language. And for environmental science, they have a criteria we call the water quality index. They can measure the water in a certain way and score 0 to 100. And if the score is less than 69, and that water pretty much not drinkable. So basically, like with this claim of the researcher, he want to show to people that the average water quality index here is less than 69 here, which is a cutoff for the drinkable or not drinkable. So in this case, the hypothesis he want to prove will be the mu will be less than 69. In mu here, the Atlanta water, the average about water quality index in the region. So this is something you want to prove. And in order to prove that, he will need to collect the data and to use statistical and use certain statistical procedure to support the claim. And that process we call hypothesis testing. Hypothesis testing. So the hypothesis is just a claim, a hypothesis, right? You think it may correct. And hypothesis testing is the whole procedure to show that, to back up your decision, to support the decision using the data. So here in the big picture, you start with some hypothesis, right? You look at the random phenomenon, you observe for a while, and you doubt a certain thing, right? And from that, you will come up with some research hypothesis. And then you will start to collect data, and then you test it. So basically, we have a three-main step. The first step is a state hypothesis. The no H0, nothing unusual, versus the alternative H1, which is something different. And then after that, we need to collect data, look at the data, and summarize the data with a number, another term we call statistic, right? A statistic is value obtained from a sample you collect, right? Sample data collected. And then we come with a question. We already know what Q1 here. Does this with this data we get it, right? The number we get from the data here look typical if H not were true. So we ask ourselves the question like that. And from that, last step, we make the decision, where the decision here will depends a lot on the cutoff value you choose, alpha. And often a universally used value is 0.05. But if you want to be more stringent, you can set it lower, like 0.01. You want to be a bit more liberty, and you can check it, set it to 0.1. So it really depends on the context. And then if the answers for the question 1 above, right? The data you collected and the statistic you calculate from the data, sample data, right? Look typical if it's not even true. This is a question. And if the answer for question 1 is no, it not look typical. It looks too unusual. And at that time you can reject A not. We learn more in detail, but here just a big picture how hypothesis testing procedure is performed. So now we look at the terminology, the alternative, and the null. So alternative hypothesis, we denote as HH or A1. Sometimes people use A1 too. Okay. So basically, it's just a claim that need to be support. Where in here, it just say that something changed, and it not include equal sign. So for example, like our Atlanta water quality index, we have mu less than 69, right? But maybe some other researcher, they may say, oh, it's safe, right? Say it's mu bigger than 69. Some people just say, oh, I don't think it's 69. It might be something else. It's not different to 69. So basically, like for our level, we look at the alternative HA like that, right? It not include the equal sign, which means something changed. And there are different kind of hypothesis setting too, but for our class, we just look at this kind of hypothesis setting framework. Okay. And the no H naught is that which is opposite of the alternative. In this case, say nothing change. But a start fact proves that their form can always reduce to the equal sign. Okay, so in this case, like the opposite of the alternative of say it's the mu less than 69, right? And basically just equal. The opposite will be mu greater than equal than 69. Another time, or maybe the opposite of mu greater than 69 will be mu less than equal 69, and the opposite of mu different 69 will be mu equals 69. But basically, like with some logic, okay, we don't discuss it here, but basically we can always reduce to the form like mu equals 69. Okay, so for the null hypothesis, you can always write in the form like mu equals something, okay, p equals something if we talk about proportion. And for our level, we just study two main testing problem, H naught versus AH for either the mean, mu, or the proportion P. We have other testing set thing too, which you can test for the variance, the median, different values, but we don't consider it here. So we look back the Atlanta water quality index problem. So in a 911 here, example 911 here, the hypothesis, the researcher he want to support is mu less than 69, right? So we look at here, right? Mu less than 69, right? And which means the no here, which is just opposite of that, right? Mu greater than equal 69. But again, with StatFat, we can always make it in reduced form, which is H naught and mu equals 69. So for this class, we just use the reduced form, okay, for simplicity. So now the testing problem we write out as the H naught mu equals 69 versus HA mu less than 69. Okay. But you should know that the actual is that just the opposite of HA, right? But we write in a reduced way. And we should notice that we have different type testing problem. It depends on the interest you want to prove. So here we just consider the mean, okay? The proportion will be similar. So here we talk about the mean mu here. So say the first kind of testing problem we call the right tail test problem, which is H naught mu equals some value. So say E naught mu equals 69, right? Versus HA mu greater than a value, say HA mu greater than 69. So if you choose your value 69, and you for sure you can change the value to the thing you're interested in, right? But we just make a number as an example. So this is the right tail test problem. And the reason we call the right tail is that basically like for this testing problem, if you calculate the test statistic, okay, and if your test statistic belong to the right side here, and basically just tell us like your HA will be more probable, okay. So this is basically just a support region for the HA, and this and the support region for HA here belong to the right side, okay. So as and because that we say it's a right tail test problem, okay. So whenever you calculate your test statistic and it belongs to the right side, and we have a certain way to decide the cutoff and where, how big is big to make the support for HA. But here is just the main logic when we call right tail test problem. But maybe if you want to remember it, easily you can also think, okay, greater than, right? Greater than, which is bigger than 0, which is the right side, right? Something maybe it's just a trick for you to make it remember like the certain faster. But the logic behind is just what I said, right? The support region belongs to the right tail. And then like we have a left tail test problem, which you are testing mu less than 69, so less than a value versus mu equal value. So which is exactly just a testing problem we just look at from Atlanta Water Quality Index. So, and the reason for the name of left tail is that again the same, okay? So when you calculate the statistic and it belongs to the extreme left, okay? It less than to a cutoff value, and here we have the red region here. So long your test statistic belong to the red region, and then you can support with confidence. You have the confidence to support HA. You can another time we call the left tail test. In another case, we call two tail test, which in you test different. So two tail test, which means you can see that it either belong to less than or belong to greater than, right? So either two extreme. A left tail here or right tail here. So if you calculate your test statistic, eventually you calculate your test statistic, and you see your test statistic either belong to the extreme left tail or extreme right tail, and then at the time you can support your HA. So this is called two-tail test problem. And here remark again, your H not always stick with the equal sign. And there's some suspect why it's a case, but basically like for our level, you just remember that. It makes your life easier when you process the problem whole, okay? But the logic is still like it's just the opposite of the alternative, okay? But you can write the reduced form, which only keeps the equal sign. So here like it just really been on a research question. So some people say, okay, they may think, okay, I don't think the underwater quality index is 69, right? So which means in the case, the research question will be the mean of underwater quality index will be different 69. But say some people say, it's the water should be fine, it's drinkable, right? So that's basically like the hypothesis you want to test, you want to support will be the mean underwater quality index will be greater than 69. So it becomes a right tail test problem. And with our researcher example, right, his testing problem is mean Atlanta water quality index is less than 69. And this is the testing problem he want to prove, right? He want to work on, which is a left tail test problem. So let us look at example 913 here. So in 1997, a random survey of 1,000 households showed that 176 of them use email. With a 0.05 significant level, the sample results are used to test a claim. Okay, so this is a claim that more than 16% of households use email. So here we talk about percent and we talk about proportion. Okay, so you have at this point you have to be very clear about when they talk about mean or when they talk about proportion. And then set up the hypothesis testing problem and determine the type of hypothesis test. So we read the problem, and basically they want us to set up a hypothesis test. And then basically when you look at this problem, you should know what the claim or what the hypothesis they point out, right? So here's the claim. And we write it out here like this way. More than 60% of households use email, right? And because we talk about percent, which means we talk about proportion. So basically this is the alternative, the thing you want to support, right? The proportion of people use email is greater than 60%, more than 60%, 16%. So which is P greater than 0.16. And when you have the alternative and your H naught will be easy, right? Just use the equal sign of this. So instead of greater, now it become equal 0.16. And again, the underlying truth here is basically the opposite, which is P less than equal 0.16, where we can write in reduced form. Okay. And one more thing. So here we set up a testing problem with a null and a hypothesis. And determine the type of hypothesis test, which means it's asked us to say out loud, right? Whether it's a right tail or test tail, right? So from here, because you're testing for the greater than, right? Greater than. So it's a right tail test. And in particular, you see it's just a one proportion z test. Okay, we will see very soon. So greater than, right? Greater than. Mu or p, right? If we talk about proportion here, it's just p greater than a value. Another example here, a Labubu shop claims that each customer spends an average of at least $30 per visit. So in this case, again, when we set that the testing problem, right? And basically you see that I think we should do the same thing here, right? Just ask, set up the hypothesis setting, right? Which put here for completion. Okay. Okay. So in this case, the claim here is that each customer spend an average of $30, right? So the mu, right? The average, right? The average spending for each customer is greater than 30. So this is the alternative you want to test. You want to support. And then like the H naught, which is mu equal 30, which is opposite, right? And this is a right tail test problem. Right tail test. Again, greater than, right? So and this is a one sample mean that, okay. So the mean testing mean for one sample here. You want to make it specific. And we have version for two sample. Okay, so say if you have two different shop, right? So they may test like this shops, people spend more on the other shop or something like that. But for our case, we just look, make an outline simple to look at the one sample case here. So let's look at this quiz. Formalize the following the hypothesis. Okay. So basically just write out what's your H naught, what's your HA. In 2008, 62% of US adults involved in charity work. A researcher believes that this percent is different today. Okay, so let us walk through this example together. So in 2008, 60%, okay, so we talk about percent, we talk about proportion, right? Proportion. So basically like at the time, 62%, right? Or is a belief that this percent different today. So this belief, right? The belief is the percent is different today, right? So basically the belief here, it will be the HA, right? P different. And because of the HA, your H naught will be And this is just a two-tail test, right? Two-tail. Different. Two-tail for proportion. So have we? Data from 2006 suggests mean phone call time. A cell phone was 325. A researcher believes that it increased, right? So what his belief here would be the HA. And we talk about mean, which is average, right? Increase, right? So increase compared to this, right? 3.25 in 2006 versus H naught mu 325. Okay. So this is the right tail test, right? Right tail test. Microsoft claims that the mean time between failures on its PC is greater than 520 hours, right? So again, here the mean, right? The mean. So they said that the average time failure between two components, right, in each PC is greater than 5. The mean time between failures, right, greater than 520 hours. So again, your H naught will be mu equals 520, right? Again, this is also right tail because greater than. A midwife claimed that the mean weight in newborn baby different 7 pounds. So her claim is that the mean weight, right? Again, this is for mean, right? Different 7 pounds, right? And your H naught will be mu equals 7 pounds. Cartabus claimed that mean lay time, right, for around 16, 11, 3 minutes. So again, we talk about mean, right? Less than 3 minutes. You know, it will be mu equal 3 minutes. And this is the left tail. Less than, right? Less than 3 minutes. This is a two tail. This is the right tail, right? Right tail. So it just depends on what is your alternative, right? So when you look at the testing problem, you should look at very carefully whether they're talking about proportion, P, or the mean, mu. And then whether they say, you know, they want to show that it's different, it's greater than, or it's less than, right? So if we make your HA. And so that's this step has to be correct. If this step wrong, and then basically like it doesn't make any sense to do anything further. Okay, so you have to be very careful at this step. You look at the problem, try to find out whether they're talking in proportion or the mean, right? Proportion, percentage, are the same thing, right? And then you should know that what they claim talk about, right? Is they talk about different, they talk about greater than, or talk about less than. Yeah, no is just a symbol, right? It's just equal sign. Now we look at step 2, where we look at data. So in step 2, basically like now you look at data, you have data, and you compute a value from data. We call a test statistic T. And the note this here, the T is chosen using the start rule under the H naught. It's just some math behind. You have a specific formula for each test, okay? But here just we talk a little bit about where it comes from. And here T will capture the key information. We need to decide, between H naught A1 and H naught AA. So here I give you a pick, kind of before we go and do to detail later in a couple, maybe, I think in a couple, maybe 5 or 6 slides, you see it. But basically, say for testing Atlanta water quality index, right? We're testing H naught mu equal 69 versus HA mu less than 69. And in section 9.2 here, you learn that your test statistic will calculate it by using X bar, which is the sample mean, subtract 69, which is the value under the null hypothesis H naught, and divide by S, which is a sample standard deviation, and divide by square root N, which is a sample size. So that's the static value we'll calculate, the t will calculate. And this t will capture information to make a decision. And then where this formula come from, it comes from just some math. Okay, we will standardize things in a certain way, and basically it's just a central limit theorem. And then in the last step, which we make a decision, we compare t to its expected pattern under H naught, if A not correct, and then the cutoff alpha we choose, and then will be two possible outcomes. The first outcome is that we will reject A naught, so which means we have evidence support H naught, A1 at HA alternative at level alpha. And the second decision will be do not reject A naught, which means you don't have enough evidence to support your alternative, your claim. So two possible outcomes here can happen when you make a decision. And here just a little bit of rationale how decision final decision were made. So basically, like it's based on the rare event rule when we talk about that last time, right? So you assume that something is true, right? But when you collect data and you see it's very unusual if your assumption is true, right? And then you reject it or not. So you remember like last time we talked about you assume maybe you have a fair die, right? And but you toss it 100 times and you see you have 99 times, you get a 6. So for sure, you can make a conclusion which is the die not fair, right? So the same thing here. So for example, here like we consider testing problem under water quality index, right? A is not equal 69 versus A is less than 69. So first you just assume here this is correct, right? But now you collect data from different location Atlanta and you measure, you see, oh, the water quality index just 10, 20, 25, 30. So I just make that kind of extreme. So which means like your assumption must be wrong with your assumption, right? Because if your assumption mu is 69 correct, so I should expect my sample water in different locations should be around that, right? Or maybe higher, right? But here I just see something very unlikely to happen if your A is not true, right? And then if that's the case, then you reject A naught and you support your conclusion. And otherwise, you cannot reject A naught, A naught, right? And attention here, we don't say what step. Okay, you can reject A naught, and you say you cannot reject A naught at significant level alpha. You don't say you accept H naught. And why we say that, because basically here the logic here that like not finding evidence against A naught and support HA doesn't prove it's right, right? It's only mean that we cannot prove it wrong, right? So for example, like you try to catch a fish, right? And you try in 10 minutes, right? And maybe 1 hour, right? But you cannot get it. You cannot catch it. It doesn't prove that the lake is empty. Right? So now we look at three different methods for making decision. So the first method we call critical value methods. And here we assume that H naught is true. So our job is that we will, under the H naught is true, we will find a cutoff which based on the distribution and the alpha significant level we pre-specify. We learn how to find this in the next section. Okay, and this will depends very much on what kind of testing you're working on, whether you test for mean or for proportion. And after you get the cutoff value, so for example, say the cutoff value is the value here. Okay, so everything here, right, bigger than you reject, right? And then you compare your test statistic t with the cutoff value, and then from that you can make a decision. If your test statistic belong to the rejection region here, and then you reject the H naught, otherwise you do not reject the H naught. We see it more in detail here, just a brief overview about the method we have to make a decision. The second method we call p-value method, which is a very it's used a lot in a practical way, and people they love it because it had a certain value inside, which is other method cannot offer. So in this case, basically also the same under assumption that H not is true, and we are trying to calculate something called p-value, which is the probability of seeing the data of this extreme or more. Okay, so roughly speaking, say if my H not is true, how likely I can get such a data, right, or more extreme. And then after you get a p-value, you compare with the alpha, and if your p-value less than alpha, because here alpha is basically just the cutoff we define extreme, right? Extreme, right? So for example, you choose then alpha 5%, and then if you get a p-value less than 5%, and then say, oh, we get such extreme, and then you reject A naught, and otherwise you do not reject A naught. And this is why the reason people love p-value, because say if you get a very, very small p-value, which is roughly speaking, say, if my data is not, if H not correct, right? And then the probability to get such a data is, say, if your p-value maybe 0.001, and the probability to get such a data is 0.001. So which means like you have something extreme, right? Because if the probability to get such a data is 0.001, and here is the first time you collect data and you get such a thing, so which means something may be wrong, right? And again, the logic here is just the same as we discussed in last time, right? About the die, right? If you assume that a die is fair and you toss 100 times and you see 99 times is 6, so something must be wrong, right? Something must be wrong. Because the probability you get 99, 6 out of 100 toss is very small. You can use a binomial distribution to calculate this probability, right? And the third method is the confidence interval, which you learn in chapter 8. And for this class, our confidence level we construct in chapter 8 can only be used for a two-tailed test. Okay. So again, here you assume H not true, and you build a confidence interval for parameter, either the mean or proportion. And then you try to check whether your confidence includes the value under the null or not. Okay. If the value under the null fall inside the confidence interval, and then you cannot reject. And it's not, and you can reject. So these are three methods, and you can use an alternate to make a decision. And another also important thing is that you should be aware you make error when you test, okay? Because the nature here is that you use a sample to make a conclusion for the whole population. So there must be error, okay? There must be error. So the truth here maybe it's not true or maybe not false. And no one knows that, right? No one knows that. But based on the data, you can make a decision you reject the A naught, you cannot reject A naught. So the case you reject A naught, but the truth A naught is true. At that time, we say we make a type 1 error, reject A naught when A naught true. And say if you reject A naught, but actually it's false, right? The truth here is false. So in this case, you make correct decision. And also say from the sample data, you say you cannot reject A naught. And the truth is that it's true. And at that time, you make a good decision, right? Correct. But say you cannot reject A naught, right? But actually, the truth is that it's false. And then at the time, you have type 2 error. So this is how people define type 1 error, which is reject A naught when A naught true. And type 2 error cannot reject A naught, fail to reject A naught when A naught false. So this is something important you have to be aware, right? When you do a testing. So for example, I consider a testing problem that the proportion of people favor candidate greater than 70%. So this case, basically you testing like P equal 0.7 versus H1 P greater than 0.7, right? So from here, you can also find out what is type 1 error and type 2 error for the test. So type 1 error is a mistake of reject A naught, right? When A naught is true, right? So the definition of type 1 error, reject A naught when A naught true. So which means that if you stay in word, will be despite the truth that P equal 0.7, but the sample don't reject the truth, right? And again, the type 2 error here, you can also specify it clearly in word, like you mistake a failing reject H naught when it fall, fail reject A naught when it fall, right? So despite the truth that P greater than 0.7, but sample evidence reject, fail to support this truth. Another example, consider the hypothesis testing problem for testing the claim that the proportion of set of medical malpractice suits is different 0.22. Formula testing problem, malpractice suits is different 0.22, right? Formula testing problem. And then what is the type 1 error and type 2 error for this test? So first thing first, right? We need to look at what is this testing problem about. We want to test a claim that the proportion of set of medical malpractice suits the different 0.22. So we talk about proportion, right? So our testing problem will be the alternative we want to support would be P. Here P, you know, the portion of set of medical malpractice suits, right? And we want to test it P different 0.22 here. And versus the alternative, the no would be just the 0.22 here, equal 0.2, always the equal sign, right? So the error we can make a type 1 error, which is reject A naught when A naught is true, right? Which you reject A naught, which you conclude that P equal P different to 0.22, right? When it really equals 0.22. And type 2 error here, you fail to reject A naught, right? Which is pretty much like you fail to reject this here, or you say you conclude this, right? When the true P different, right? So let's look at this quiz. A researcher claimed that more than 65% of college students will graduate with debt. Determine type 1, type 2 error in this scenario. So this is kind of problem, right? To make it correct, the first thing is that you have to say the testing problem correct, right? Otherwise, you specify the wrong error. So it's important to specify H naught and A1, right? And again, if A naught and A1 you specify wrong, which means there's no point to process things forward, right? So this must be correct. The first step, HA A1. So here we care about the percent of the proportion, right? More than 65%. So here the claim the researcher want to say more than 65% of college student will graduate with debt, right? And H naught will be the same, right? So this is a very important step. You need to make it correct, okay? What is problem about? Mean abortion, and then whether it's about greater, less than, or different, right? So this is basically just a tail, right tail test, right? And the type 1 error is the error reject A naught, right? Reject A naught. The when in fact it's true, right? So this is type 1 error. And type 2 error is the error you fail to reject A naught, right? When it's true. So basically, we can also, in fact, when A naught 4, I'm sorry, which means A1 true, right? P greater points. But we fail to reject H naught, right? Which means we didn't support this, right? P greater than 0.65. So you just refer back, right? Fail to reject A naught when A naught is false, right? Which means like, in fact, this guy is true, but you fail to reject A naught, right? And you can just try exactly fail to reject P equal 0.65 when in fact P greater than 1.65. Here I just put in the backward direction here.